characteristics of the 7483 IC. IC 7483 is a 16-pin IC, and it consists of 4 full adders which are interconnected to each other, and the A and B and C in 0 represents the inputs, and whereas the S and C out 3 represents the outputs. And the 7483 full adder with carry in and carry out feature can also be cascaded. Obviously, whenever we are using ICs, that can be cascaded. That means added with more than one ICs to represent larger circuits. How it's done, I'll show you in a while. This is the basic diagram of IC. See, just memorize it and just draw it on your copy, whatever you may like it. I'll provide you the, this PPT, obviously, but you have to just think of it. See, this B4, see the pins. This is ground GND, pin number 12. Okay. And this is 5. Pin number 5 is VCC, which will give us power. Pin number 1, 3 and 8 and 10. This will represent the higher order bits A1, A2, A3 and A4, and B1, B2, B3 or B4 are represented through 11, 16, 4 and 7. These are 4 inputs, and C0 is the carry output, and C in where is C in, where is C in? Wait a moment. These are the outputs. See, summation sign. Bit 4 output is summation of 4. Bit 3's output is summation of 3. And bit 2's output is summation of 2. And bit 1's output is summation of 1. So this is the IC, and C4 is the, C4 is the carry input and C0 is the carry output. So this is the pin structure of the 7483 IC. Now, this is the table for pin description for all the pins. You can memorize it, you can write down it, whatever it is convenient to you, you can do that. Now, I'll move forward to full adders truth table. This is the truth table. I know you guys already know about the truth table thing. Still, I'll explain it to you. Whenever we are inputting, this is a full adder which is adding 3 bits simultaneously. That is 0, 0, 0. We already know the binary addition, which is 0, 0, it will give 0. 0, 1, it will give 1. 1, 0, it will give 1. And 1, 1, it will give 0. But carry will be 1 and that will be forwarded to the next bit. So here it is 0, 0, 0. 0 plus 0 is 0. 0 plus 0 is 0. So carry and sum both are 0. Now 1, 0, 0 will give us 0 and sum is 1. 0, 1, 0, only 1, 1 is there. So if whenever more than 1 ones are there, then only carry will be generated. So we don't need to worry about these single ones. Whenever this is single ones and other than the 0, then the sum will be 1 and the carry will be 0. And for 2 ones, see, for this one, 1, 1, 0, it will be 1 plus 1, 0 and carry will be 1. That's why carry is 1, and 0 plus 1 will be 1 and still carry is 1 and sorry, my bad. 1 plus 1 will be 0. Sum will be 0 and 0 plus 0 will be 0. So the sum is 0, but 1 plus 1 has the carry is 1. So the carry is 1. So this is the addition, and this is how it's done in every bit. This is the truth table. Now we come to our first experiment, which is 4-bit parallel adder. This is the block diagram. We don't need to look at this right now. This is the digital circuit. 4-bit parallel adder consists of 4 full adders. What I have already said, that our IC, which is 7483, consists of 4 full adders already. So we don't need to add any more circuits. We just go to the direct circuit and direct to the IC and connect it as per its requirement. This is the circuit diagram of using the IC. See, I am drawing it on the Proteus so that you can learn it. Okay, I am sharing the screen with you. Wait a moment. Just wait. Yeah. Now is it visible, guys? Students, is it
Yes,
visible?
ma'am.
Okay, okay. Okay.
Yes,
Now,
ma'am.
how to work in Proteus is, how to work in Proteus, first we need to, okay, first we need to learn how to pick paths. First, see the block diagram. Just wait a moment. I need to share both of this. Okay, wait a moment. I'm sharing the in the chat box. The oh, there's no facility. Actually, wait a moment. Yeah, is my screen is visible, student, to all of you? Please tell me, then I can share more. Okay.
Yes, ma'am. It's visible.
Yes, ma'am.
Okay.
Yes, ma'am.
Yes,
See
ma'am.
the you can see the
Yes,
logic
ma'am.
diagram over here
Yes, ma'am.
in the PPT, and I
Yes,
am
ma'am.
just drawing by
Yes,
seeing it. Okay, I am just drawing it by seeing this logic diagram. You have to follow this. Okay. First of all, what does we need? That is the this IC 7483. Now, where did I get from it? We'll go to the pick parts. Now, this is the tab for pick parts. This tab is for pick parts. We'll click it, and here we will write 7483. Hold on a moment. This will come. Yeah, see, we'll take the second one, 74LS83. Basically, these are no difference. We have used this one because I have practiced in this one. These are both are IC. LS83 or 7483, both are IC, doesn't matter. So I am taking this one. Okay. We have to click twice. First, it will come as a skeleton. Then I'll click again. This will come as a circuit. Now, what we have to do is take the power and ground. Now, power and ground will take from this part, terminals mode. Hope this is visible. This symbol, just memorize this symbol, terminal modes. Click on it. See here, power is written. I'm clicking on power, and I'm just twice clicking, double clicking here, and power has come. And I'm clicking on ground. We need ground for 0, and I'm double clicking here, and ground has come. Now we have to connect it. Suppose we want to give the input of, this is 4-bit. This is a 4-bit. First binary number will be 4-bit, and second binary number will be 4 bits, right? So for first binary number, let us take, just write down in your copy 1111, and for the second bit, A will be 1111. I am telling you from MSB to LSB, that is A3, A2, A1, and A0. That will be 1111, and B will be B3, B2, B1, and B0 will be 0011. So if we sum them, just add them on your own. I'll just doing it my in copy. That will be 001. Okay, and do one thing that will be easy to learn first. First step as, do one thing. A will be 1111, and B will be 0001. From B3 to B0, I am telling you 0001. B3 will be 0, B2 will be 0, B1 will be 0, and B0 will be 1. Write down and add them. Write down and add them, and put down your sum and carry. Write down your sum and carry. It will come hopefully.
Can you just repeat the numbers?
Yeah, for A it will be 1111. From A3 to A0. A3 is 1, A2 is 1, A1 is 1, A0 is 1. Understood?
Yes, ma'am.
Now for B, B3 is 0, B2 is 0, B1 is 0, and B0 is 1. Clear?
Yes, ma'am.
Okay, and now the sum will be, please do the summation. The sum will be 0 0 0 0 and carry will be 1. Just check it if I am right or not and tell me.
Yes,
Yes,
ma'am.
so the if we construct the circuits, if we construct this circuit, what we have to do is, for A, this, see, you can see the A1, A2, A3, A4, we have to connect all of this to power. Power means 1. So I am connecting all of them. See, I am just dragging it and connecting. Just click it. I am just dragging it and connecting it. Just drag and connect by clicking. And same for this also. Oh, sorry. Drag and connect. See, 1 1 1 1 has been done with A. Now for B, what is it? 0 0 0 1. So B3 is 0. B3, B4, I mean B3, B4, B1, B0 I have taken. Here B4, B3, B2, B1 is written as it is. Nothing wrong. So B4 is will be 0.
Again, repeat how you did that. This part again, repeat it.
Which part? Please tell me clearly.
And this
Which
whole
part?
part, this whole part.
Just connection. The connection I have done.
Yes, yes, yes.
This is the power. This is VCC. That means it will give us 1. And this is ground. It will give us 0.
Yes, ma'am. I
Then,
am telling about yes that one means if after this IC you connected this. That is why I'm tell that one. I'm telling how you did that
okay,
one.
I'm again connecting the B part. Then just see this. Just drag. Just put the pointer over here. B1. B1 is 1. So we will connect B1 to VCC. See, I'm just dragging it and just click one click. See, one click. Again, these 3 bits will be 0. We'll just drag it and connect with one click. Whenever this is attaching, just click here. Just click here. Again, for B3, it will again be 0. So we'll just connect to this where this is showing the 0. Just connect it and click it. One click. Just attach it and click. Just attach it, slowly attach it to this where and one click. Now you get it?
Yes, ma'am.
Whoever asked me the question? Okay.
Yes.
Now, see, the bits has been represented. They are 1 1 1 1 for A, and for B it is 0 0 0 and 1. But we need to represent the outputs. How we can represent the outputs? We'll use LED lights. Now LEDs are part. We need to go to pick parts again. Now we'll search the LED. See, several LEDs are coming. I'll take this one, this active one, LED Aqua. Just remember the name. This is animated. That's why I am taking it. Nothing special. This is animated. This will show us specifically how to use it. That's why I am taking it. LED Aqua. Just write down LED Aqua Active. Okay. Just write down the name. So that and memorize the picture so that you can draw it on your own when you are doing at home. I have selected it and just double click it. See, LED has come. How many LEDs do I need to put here? 4 for sum and 1 for carry out. So 5 LEDs. See, 5 times I am double clicking. 5 LEDs presented. Now, what we have to do is, we need to connect. These are, see, S1, S2, S3 and S4 our sum. And C4 is our carry out. So what we have to do is we need to first connect this S1, S2, S3 and S4 to the LEDs. First one is connected to this one. Just attach and just click it. Second one is connected to this LED. See, I think this should be a little.
Ma'am,
Yeah, tell
please
me.
increase the size.
Tell. Yeah, I'm trying to do it. With the Zoom. Yeah. Oh, sorry. Yeah. Now is it visible?
Yes,
Yeah. Is it visible, guys?
ma'am.
Okay. First of
Ma'am,
all,
can I get logic
just
probe and logic step to get the input output?
sorry. Please repeat.
Can I get logic probe and logic step to get the input output? Uh,
Why would you do that? You just have to put the LEDs, not logic state or something. You just have to put the LEDs right away. That circuit will run on in its own. I'll show you the whole part, then you can understand it properly. Okay, just keep patience.
okay.
Now we have to connect this one to this LED, and now this one to this LED. Now this one to this one. Sorry, just delete it. And this is our carry output, which will be added with this one. Added, just attach and click. Now we have to, what we have to do, see, for full adder, it is mandatory to keep the carry in to ground. When you see the Salivahanan book, you will get the, get the block diagram as I have shown in the PPT also. Let's get back to the PPT. See, C in here will be grounded. Okay, it's not shown in the block diagram here. You will go to the Salivahanan book. I hope you guys are following that. That will show that C in will be grounded for parallel adder, 4-bit parallel adder. So I have make this grounded. And now this LEDs, these has two part. See, this will be grounded too. Otherwise the circuit will be incomplete. Now we have to do the ground part with this. See, this is the ground. Just attach it and click. This round thing means the circuit is okay. Okay. Now again, this part we'll just attach it and do this. And same for the rest of the LEDs. One will be presenting the output and the another one will be presenting the ground.
Ma'am, can you just repeat why we are grounding LEDs?
LEDs has two inputs. If we don't ground this one, then the circuit is incomplete. The circuit, it doesn't know what to do with this input. It doesn't know what to do. That's why we have to ground it, and it has to work only one input. Whenever we are using two inputs, then we don't have to ground it. Otherwise, the circuit will be incomplete. So that's why we are adding this one also. All of them are connected to ground, so doesn't matter what I am connecting to. And this is also with ground. See, you can connect with ground one wire with one LED, and rest of that will be added with one with another, because this line is representing the ground, this line is also representing the ground, this is also representing the ground. Now when we have to just you see the circuit properly, because I won't be able to save it, because this is a demonstration version. I have to download it in a rush, because you have those classes. Otherwise I was instructed to use the circuit verse, but I like to use this IC. That's why I am using this demonstration version. Whenever I am running it, if I am running this circuit, let's see what it come. See, which LED is enlightened? This one, D5. Look at this. What is our carry? Carry is 1, carry out, right? Carry out is 1, and all the sums are 0. That's why the sums LEDs are not enlightened, not blinking, and this one is blinking. That meant our circuit is proper. One more thing I'd like to tell you, this red boxes mean the LED is active, and this blue boxes represent the LED is inactive. And if there is any gray box, that means the LED is not grounded. I mean, the circuit is incomplete. Now you get it? Clear? Everyone?
Yes, ma'am.
Please tell me.
Yes, ma'am.
Yes, ma'am.
Okay, okay. Thank you. Okay, this is one circuit. Okay. Another one I'd like to show you. I can't save it. Okay, do you want to click a picture or something? You can click a picture. Whenever you are done, please tell me. I have to erase it. Okay.
Ma'am, we are done.
Can you tell what is the name of the?
You're done? Okay, okay.
Can you tell what is the name of the?
What?
Ma'am, the name
What
of
is
the
the name of
LED.
what?
Ma'am, LED.
LED. Oh, active aqua. Active LED aqua. LED aqua active.
Okay, ma'am.
Okay. Okay. Now I'm just erasing it. I mean, I'm doing a new project. So okay. Now this is, I'm already tired. Okay. Fine. This is the first experiment. Now the second experiment will be the 8-bit parallel adder. See, I'm just showing you the schematic diagram only for this one. Rest of you will practice at home. Nothing else I'm going to show you, because one circuit is more than enough to, judge the parameters and all. So this, I'll just show you how to draw this circuit diagram. Next two experiments will be remaining, and that will be taught by Shuchira ma'am when she comes, and then we'll just continue to giving you assignments. Okay, first of all, we'll take two ICs. So we'll go to pick paths. 7483. See, I'm going to select this one. Just mark it 74LS83. Okay, just write down in your copy. 74LS83 will take. Okay, we'll just select it and click OK. We'll just first click here, then second click. Then we need to cascade, so we need another one and click it. Okay, now I am just zooming it so that you can understand.
And which one you are doing now? 8-bit adder.
Yeah, just hold on a moment. Yeah, 8-bit I'm doing is 8-bit parallel adder by cascading 2-bit to 4-bit IC. Okay, now
No.
okay. Why isn't it coming? Now it's okay. Now what we have to do again, we need to pick parts. First of all, we need to put the VCC and ground. VCC is power. We have put power over here, and we'll take ground like this. Okay. Now follow the diagram. Cin will be grounded, and see, Cin will be grounded, and just as it was at the first circuit, instead of 4-bit, the 8-bit some bits will show us the output. So we need to connect LEDs, 8 plus 1 for carry out, 9 LEDs, and we need to connect this 8 plus 8, 16 bit. 8-bit parallel adder means what? 8-bit first bit, second binary number is also 8-bit. 8 plus 8 total 16 bit. So that's why we are using two circuits. Now we have to connect each one of them to proper in a proper manner. First, we take the LEDs from pick parts. LED. We are taking which one? LED aqua active. LED aqua active. Okay. How many LEDs we will be needing? I told you 9. Now you may ask me, just double click these. How many ingredients? 6, 7, 8, and 9. You may ask, ma'am, 2 C outs are there in these ICs. You have to just cascade them. There is how the cascading is done. Otherwise, the cascading will be done. The cascading will be helpful with these C4 and C4. I mean C outs. So we'll just connect them. First, we'll just connect them. This is how the cascading is done. And now we have to put the LED with the LEDs to the sum. See, I'm putting it. Each and every LED will have each and every bit. Just put them accordingly. Just concentrate how I am making the circuit. Just follow that. It's very easy, very, very easy. These needs to be connected. Again. See, I am just connecting it by attaching and clicking. And this will be for this one. Sorry. Just connect this one. Now the LEDs of the outputs are connected. Again, what I have to do is connect with the ground. Now I am taking another ground so that it will be easy to another ground for ground, and just putting it here, and I'll connect the second input of the LED to this ground. As I have told earlier, every LED has two inputs. We need to put at one of them to the ground. Otherwise, they won't work and the circuit will be considered as incomplete. So I'm just
Ma'am,
connecting it to the ground. Tell me,
why are we
tell me.
connecting both the C4 to the same LED?
Because that is the cascading. What I have told you, see the block diagram. We need two ICs. First IC C out will be the C in of the second IC. Sorry, I have made a mistake, I guess. Oh, sorry. This won't be like that. Okay. Just sorry. I beg your pardon. Just delete this. Yeah. C4 will be connected to the C in of the second one.
Yes,
C.
ma'am.
Okay. Sorry. Thank you. Whoever. What's your name, by the way?
Ma'am, Madhushri.
Thank you. Madhushri. See, we have similar names. That's why you are so intelligent. Thank you so much. Okay. Please go. Why isn't it going? Please hold on a moment. Not working. I have to delete it. Yeah. Now it's okay. Now we what we have to do is give the inputs. First, we need to suppose I am giving the input like first A1 to A0 to A7. I mean A1 to A8 will be 0 0 0 1 1 1 0 0. Please write down 0 0 0 1 1 1 0 0. A1 to A8. Okay. And B1 to B8 will be 0 0 1 1 0 0 1 1 0. Okay. Sorry. 0 0 1 1 and 0 0 1 1. B1 to B8. I'm repeating myself. A1 to A8 will be 0 0 0 1 1 1 0 0. And B1 to B8 will be 0 0 1 1 0 0 1 1. Now, I'll just connect it with according to that. A1 to A8 is A1 to A4 is 0 0 0 1. So I'll just connect to A1 to 0, A2 0 0 0 1 is it. So 0 0 0 and 1 will be connected to VCC. VCC. Okay. Now A for this one, it will be 1100. I hope you can connect with me. Sorry. 1100. So 1, this one is 1, so I can connect it with this 1100. 1 1 0 0. Now for B, what it is 0011. B1 to B8, B4 is 0011. So 0 0 for 1, it will go to write this 1 and 1. Please follow. Are you following? Students, please respond.
Yes, ma'am.
Okay. 0011 and now again 0011 for these 4 bits. So this will be connected to this one directly. This is also 0. 1 for 1 it will be connected to this one. Suppose here and oh, to this one. Okay. Hope the circuit is complete. No, not completed. C0 is not connected. C0 will be ground. This is the first C in, so it will be grounded. Okay. Hope this is okay. Now let's run the circuit.
Ma'am, the upper LEDs
Yeah,
are
tell
not
me.
grounded. Upper LEDs are not grounded.
Okay, thank you. Yeah, see, upper LED is not grounded. That's why it's showing the gray light. See, inactive. So I'm just stopping it and again grounding it. Thank you. Thank you so much. Okay, let's ground it. Done. I guess done. Is it done? Please tell me if I'm wrong, okay? I
Ma'am,
won't
there is
mind that.
one LED. Okay, okay, that's done.
Okay, fine. So this is how the circuits are meant in Proteus using 7 please follow the block diagrams and you have to draw the circuit which will be done in the training, which will be done Zorget IC, which number is 7486. We can use that IC also to represent this circuit, which is a full circuit, which is a full circuit. So you have to follow what Shruti said to represent this circuit. Any questions until now? Is there any question?
No, ma'am.
Okay, fine. I hope there's no question. Okay, thank you. Okay, let me see if Shuchira has come or not. Okay, I'm just stop sharing right now. Shuchira ma'am will be there in 10 minutes. Okay, let's do one thing. Shuchira ma'am is not yet come, so I'll just continue. Try to make another circuit. If she comes, then she'll just take over from here. Okay, I'll just present. Yeah, hope you can see my screen. So the next one is 4-bit full subtractor. Let's see what it does. First one is we need to take the IC. Let's take it. Go to pick paths. Seven four eight three. Okay. This is my IC. Let's zoom it. Yeah, this is the IC. Now, this is our 4-bit for input. Say the 4 bits are 1111. Just write down. I'll take the VCC, the higher order 4 bit, from which we have to subtract A minus B it is. So A1, A2, A3, A4 will be 1111. Please write down. A1, A2, A3 will be 1111. So we'll connect it to this. Done. Now we need to think about, first we just do the LEDs. LED. See, LED aqua active. How many LEDs will be there? Just see the block diagram. 4 and 1, 5. 5 LEDs we will be needing. 1, 2, 3, 4, and 5. Let's take ground. 2 grounds will take for clarify. 1 ground will work also. Doesn't matter. Just make the circuit clear so that you can understand. So we'll connect the one input of the LEDs to the ground. Just follow me. It will be helpful. So all LEDs are ground. Now connect the LEDs with this. See, done. Now for the lower order bits, what we have to do is take the XOR gate. Take the XOR gate and connect the C in with the one input of the XOR gate. And the other input will give us the B0, B1, and B2 and B3. Okay, fine. Then first what we do, take the XOR gate. Just hold on a minute. Let me see Shujira has come or not. Just hold on a moment. Yeah, Shuchira ma'am is coming. So we are just stopping right here. She'll continue. I hope you got the basic idea how to draw it. Actually, I could have completed it, but she has told me she'll just make you understand this. That's why will be a very big confusion if I continue this. Just wait.
Okay. So good. Okay.
Yeah.
Yeah. So good. You can hear me? You can.
Yes,
Yes,
Shuchira,
ma'am.
I can hear you. Rest
Okay.
of
So may I know how far we have already completed?
Yeah, I have taught them about the IC and shown them how to do the two experiment. First two experiment, that is the first one is the 4-bit parallel adder using the IC of 7483, and the second one is 8-bit parallel adder by cascading two 4-bit 7483 ICs.
Okay.
So I have shown them how to do it in Proteus
Okay.
and with screen sharing,
Okay.
and rest of the two experiment will be continued by you.
Okay. Okay. Thank you, Madam.
Thank you, Shuchina ma'am. I'm just muting myself. I'm just watching.
Okay. Okay. So I'll be presenting my screen. Okay. Just give me a minute. I was in another class, so I have to open the files and all. You can see my screen.
Yes, ma'am.
Yes, ma'am.
Okay. Okay. And let me open the Proteus. Always, you all have Proteus. You're comfortable with Proteus, right? I
Yes.
think in the
Yes, ma'am.
yeah, in the digital lab also I think you're using. Always run as administrator. And okay, so here we go. You have done up to here, right? You understood this full adder, right? Completely. 7483. Okay, now we will continue from experiment C 7483 and 7486 will be required. Okay, 7486 is for surrogate, but in Proteus, you won't have an IC like you have for full adder. You will have to use some logic symbol kind of thing for simulation. Okay, I'll show you. Okay, I'll explain the concepts first, then I'll go to the circuit. Okay, so what we'll be doing first is first thing we'll be doing is how to, okay, you may reply me. I will just ask you a question. How to, sorry, this is from the past class and calculate whose complement using a XOR. Okay, before that, the main problem, how to implement a subtractor using a full arrow. Okay, this is what is our main focus. Okay, main focus. That is, we want a 4-bit subtractor, but we'll be using the IC for full adder that you already had been using. 748. Okay, so I'll just, you know this already, I'm sure, but I'm just repeating it once again. Say, can we basically express a subtraction expression like this as addition? That is very simple, right? Yes, we can. This is in decimal. We can write like this, right? Then, if I have to do it in binary, the first number A, say first operand, it is 15. Let's express it to binary, and second operand has to be -3, and then we know that any negative number in binary we can represent it using its 2's complement, right? 2's complement. So what we are going to do is we'll focus on this second problem, that how can I calculate 2's complement of a binary number, and we'll be using a XOR for that. So is it possible? Do you have a clue how to do it? Or is it really possible to do it? Can XOR get help us to find a complement of a bit? Please respond. Can we use XOR get, or how it will work then? Okay, let me just give you a bit more clue. Okay, so how we perform a 2's complement? We first make 1's complement of the number, right? 1's complement. So in this case, we have, say, the unsigned value of b. You may say the mod of b is 3. So we take the 3 is your in decimal, and it is like 0011. So we can take 1's complement of 3 as 1100, like this, correct? And then to find the 2's complement, what we do? We add 1 to it, right? We add 1 to it. So, sorry. Right? And then what we get as 2's complement? 1, 1, 0 1. Okay, so you see here is an addition, there is an addition and a complement operation. So the point is addition is very simple. We are already using an adder. So that's not a challenge. The only problem we have to solve is how to complement the bits. Okay, and that too using a XOR gate. Okay, so that is how the problem reduces to only just complementing the bits. And just tell me how you may do this. You have already covered in the theory class, right? Anybody, please respond. This is important. Like, to interact. I mean, any just if you cannot uh, find out, you can tell me that, then I have to proceed. No guess, nothing. Okay. Let me give you some more clue. Let's look at the Zorget table. Okay. And the Zorget truth table says, let's name it, say x1, x2, y. Okay. You know the truth table, right? When two bits are similar, we have a zero output. And when two bits are dissimilar, like one is 1, another is 0, or the other way around, 1 0 or 0 1, like that. So in that case, it will be 1, right? So for 0 0 and 1 1, the output is going to be 0. And then for 0 1, then for 0 1, it is 1, and 1 0 is 1. Okay, so any idea? Now it is simple, right? Simple, no? You saw some pattern. Hey, respond, please respond. Otherwise, the class is very boring.
Please respond to ma'am. Otherwise, how can we understand you are understanding or not?
Okay, I think nobody could
I think
figure out.
direct
Nobody could figure out. Anyway,
understood. I think I one person is telling something.
she's saying, yes, ma'am, understood. No, I'm asking whether you can figure out. You need to respond at this question. This question. Whether you need, whether you can explain me that how Zorgate can be used to make a complement, to perform a complement operation.
If you don't know the how it is used, then ask ma'am. She will explain.
It's okay. That's remember. Yeah, they respond. Okay, let them. I'm giving you say 1 minute time. Okay. See, that is the key of this experiment. That is only simple thing, and that too will be done in Notepad. That is the most interesting thing. And once you understand, the circuit is very easy, super easy. Okay, I think this quiz is over. I'm telling it. I cannot wait say forever. See, can you like, yeah, can you like see it? See the pattern now? See, when the second bit x2 is kept 0, okay, x1 remains in the same state, okay. Then when, let me write in English, okay? If x2 is 0, then y is equals to x1. Whereas, if x2 is kept 1, then the XOR operation will have the output as complement of x1. Okay, clear, right? Whenever I am applying x2 as 1, x1 value is getting complemented. If x1 is 1, the output will be 0, that is complement of x1. And if x1 is 0, then the output will be 1, that is the complement of x1 again. Okay, and if I keep the value of x2 0, then the output is going to be x1 itself. That means the state does not change. Whatever the value of x1 is, the XOR output is the same. Correct. So just remain these two lines in mind and we'll proceed towards the experiment and designing the circuit. Okay. Okay. So where did we leave? Here. So we can easily find one's complement of a number, 4-bit number. Then it's easy, right? How? Say we have this number positive 3 plus 3, and we want to find out one's complement of 3. So we have say 0011, okay, as the B input, the second input. I'm writing like this, okay, and then I will perform a bitwise XOR operation. I give this mark operator sign here, bitwise XOR. So bitwise means each pair of, it will act on every pair of bits, okay, and I will operate. This second operand is always 1 1. That means as this is a 4-bit number, I will apply bitwise OR with 1 1 1 1. Okay, the second operand of bitwise OR is going to be all ones. So for n-bit number there will be n ones. Understood? So what is the result of bitwise OR in this case? Bitwise OR result will be 1 1 0 0. Right? So let's just make it x2 and we write in this way, B input and XOR, bitwise XOR x2. There, writing it. Okay. So now we have to see that how to find the two's complement. This is very simple, right? So once we have obtained one's complement from this operation, the second operand input with bitwise XOR, we also add 1 to it. Okay, we add 1 to it, and you see this is basically, I'll not write here, write separately. So let's say we have this and we have a adder, so we'll do the operation like, the circuit is going to follow like this. First operand A, okay, next what I just wrote that we have already found, the complement B input XOR x2, and here it is 1100. That is one's complement of 3, and then we will put C0, that is your carry input in the adder. Okay, carry input in the adder, we have seen it already, as 1. So you have seen, you might have noticed, right, when we perform addition here, say here, this C in remains 0. When we simple addition will always have C in 0, because there is obviously no other stage on the left hand side of this adder. So this is the lowest bit. So that's why there is no carry input coming in. So that's why we make it 0. But when we are trying to make a subtractor using the same circuit, we need to add an extra 1 to get the 2's complement. That's why we set C in as 1. Okay, it is not like the carry. The purpose of setting 1 does not mean that it is a carry from other stage. It is because we need to get the 2's complement of the second operand, or yeah, say for the B part, when we are performing A minus B, then that one will be providing with C in. Okay. Then if we calculate, if we perform the addition, definitely you will get what you'll get. Let's see the sum 110, then 110. This is 1. This is 111, and another carry. So there is a 4-bit sum. There is a 4-bit sum and a carry, right? And if you take the decimal value of this sum, this 4-digit, what is the value? This is 12, right? And when we perform such an addition, such a subtraction with say 2's complement form, we generally discard this carry, or we ignore this carry. Okay, so forget about this carry. This carry does not mean anything. We will simply focus on, but this carry will anyway appear in the C4 line of the adder. Okay, so the C4 line will have carry 1. In this case, this is C4, and rest of the thing will come as the 4 sum bits. Okay, but we will in this case discard the carry. Okay, and only the result will be the result. You cannot see. The result will come in the S pins only. Okay? That is the concept. Okay, so you can understand from this that how we are going to design the circuit, right? We are going to apply a power voltage from high voltage to C0. We are going to apply the original B input bits to a XOR gate and complement it, and then that complemented bits will be applied to the IC, and the A bits will be applied to the IC as we were doing before. Okay. Okay, let me see what you're asking. Hold on. Yeah. When both inputs are same, then output will be 0. That is correct. Okay, is there anything else that you want to see? That is actually Sukanya, right? Sukanya was guessing it right, like she was on the right track, kind of. Okay, that is a good try. That is you tried. Okay, so I'll go on explaining the circuit, or you have some confusion here till up to here. You got the logic? What we are going to do? Yes, no, maybe, yes, yes, yes. Okay, please don't be shy. Okay, don't be shy. Even if it is very simple thing you are not getting, I'll explain again. Okay, okay. So anyway, people are saying yes so far. So I'm going to show you the circuit now. Okay, I'll make the circuit from scratch, or you'll be able to understand. Okay, I'll show here.
I would like to interrupt you for sorry
Yeah.
for interrupting.
Yes,
I
yes.
think you don't have to make the circuit from scratch. I just have shown them how to make a circuit, how to pick parts and all everything. You just explain it because you have to explain one more experiment also. That's why I'm suggesting it's just a
Yeah,
suggestion.
yeah, yeah. Yeah, thank you, thank you. Yes, I'm not going to do everything. I'll show you this XOR connection, okay, how we are
Yeah.
applying it. Yeah,
Okay. Thank you, Shujit. I'm
yes,
muting myself.
yeah. Okay, thank you, Manthasri ma'am. Yeah, I'll show you. So this part you know, this connecting to LED part and everything you have done. So I'll just show you this part. This is a bit anyway messy. So let me delete it. Delete the wires. Okay. Okay. So you see, hold on. Yes, here. You see, this is a circuit, right? So this A is going to be this A that we just showed, the first operand, this one. Okay, that is simple connection. There is no problem in it, right? It is easy. The second operand, however, which is the negative one, negative number, that needs to be complemented and then, excuse me, so that needs to be complemented and applied to the adder, right? As we saw, so this gives us the complement. B input is the original value. Say we have 3, we have to subtract 3. So it is what to say. Uh, it is the modulus. You know the modulus, right? So we are like without considering the uh, sign. It is the magnitude, right? So this B input is that magnitude. Okay, and for 3 the magnitude bits are 0, 0, 1, 1. Okay, so from higher order to lower order. So let me see how it will go. This is B4 is higher order bit and B1 is the lower order bit. So how I'll show it. Sorry, let me move them. Okay. So the original data value inputs will go in the inputs of XOR gates. Why 4 XOR gates are needed? Because we are performing bitwise XOR. Okay, so there are 4 bits. So for each bit, we need a XOR gate to complement that particular bit. And the complemented bit, see, I have labeled it here clearly that that is coming from the output of the XOR gate for each of the XOR gate. So like it is here, say for first bit it is B1 complement, and then Here, if I place it, we'll get B2 complement. Okay, from white. Okay, so in this way, B1, B2, B3, B4, each will be complemented by these OR gates. And so let me apply the values. Okay, 1100, right? So these, sorry, I'm wrong. 001, it should be. Yeah. So 3, right? So 2 lower bits are. So let me design it. I'm going to put the second on the second pin the B inputs. So, so where a bit. I think I'm going to take another power.
Ma'am,
This is
open
the
the
power.
and beside the zone gate, on left hand side of zone.
Sorry. This. Sorry. Can you repeat again?
What is this B1? On the left hand side of zone gate.
Yes. I have labeled. This is just a label. Okay. To mark that I am putting the original value here. Okay. Actual input value. So I'm going to put the B inputs on this pin. Okay. 0011 and oh, there are so many. Okay. I have, and this pin is 0. It should go 0. Drag it a bit. And this pin. So just check it again. We have got 0011. Okay, the original B. And the other, you see the notepad here. The other, for complementing, we need to set all other inputs for the XOR get 1, right? So the other inputs will be 1. So this is a positive power circuit. So PCC, I mean. So all other input will be connected to this line. Okay, cool. So this is this is going to calculate for each bit. We are going to get the complement, and each complemented bits of B will be applied in the IC. This B input of IC. So what effectively we are getting is this portion. In the notepad, just see, we are getting this. Up to this we have done. Okay, A we have provided and we have provided B complement. Now we have to also provide C0 as 1 to calculate the 2's complement. Good. So now C0 is not connected. So I'm going to connect this VCC line. This is also power. These triangles are power. Okay. And these are just labels. Okay. I just use them to label that what is the pin all about. Okay. Good. So the circuit is ready. These pins are already connected to LEDs. Now let us simulate it then. What we have got? This is the carry bit, right? C4. See, you can see, right? C4. This we need not consider in this case. Need not consider at all because we are doing just a subtraction. that too using two's complement. So the output we want will come here in this 4-bit sum, and it gives me, see, the LED on means high power, so 1100. That also we got here 1100, that is in decimal 12, right? So 15 minus 3 is 12. So it got verified. The circuit is okay, right? So I'm stopping the simulation. Question: any problem with the circuit? Reflect. Are you doing parallelly, or you're just looking at it? Because there is, I don't know if Medhashu ma'am has already showed you. There is a long list of experiments, and then you have to submit the assignments also on 13th. Okay, and there you have to give the screenshots of what you have got. Results will be providing, like if you're, like I just did, right, 15 minus 3, so you'll be writing like that. Okay, input is 15, so you'll write that this A input is 1111 and B input is 3, okay, 0011, and what output you're getting after applying it to the circuit. Okay, so in that way you have to prepare the assignments. Okay, so I'll suggest you understand it very well right now. We still have some time. Okay, the next experiment just follows this. It's just a single change that we'll be doing, and we'll get a new circuit altogether with new functionality. Okay, so is this part clear? Reflect a bit, okay? I'm not getting any response from you. I just took another class of the same lab. Uh,
Ma'am, I have a question
yeah,
regarding the assignment submission.
sure.
Ma'am, actually, previously Nilanjan sir told us to submit all the assignments in one PDF file. So, ma'am,
Okay.
do we have to submit the combined PDF file consisting from assignment 1 to 7, or we will only submit assignment 7 by Sunday?
You just submit assignment 7, okay? And then for all other assignments, I think we have to, yeah, I'll create a separate Google form and separately I'll take that submission, okay?
Okay, so ma'am,
You
this
just,
Sunday we will only submit assignment 7.
yes, okay?
Okay, thank you.
Shuchira, should I give
Ma'am,
the
what are
link of the attendance?
Yeah, please,
Shuchira ma'am?
you should.
Okay.
Yes,
Okay.
please. It's
Okay, ma'am.
already,
ma'am,
yes,
ma'am,
tell
what
me.
are the assignment questions?
The same
Assignment questions
experiments.
will be given. Will be given in the PPT. I'll share the PPT in the Telegram group right now. We'll find out. You'll find out in the first page. The same question.
No,
Okay.
yeah, same experiments we are doing now. Okay, there is nothing like
I'm going to
extra.
submit. I'm going
Yeah.
to submit assignment.
Okay, let's have questions regarding the experiment. Ishita, what you're saying, I cannot hear you properly.
Ishita, we have written in everything what you have to submit in what format. Everything is written in the PPT itself. I am just posting the PPT in the Telegram group, so you don't have to worry about it.
Oh,
Okay,
Medhashu
ma'am.
ma'am, we will.
Yes, Shuchira ma'am?
I already have a zip file ready. Okay, I just like
Okay,
given
okay.
it.
Then you post it.
Yeah, I'll post it. Okay, let's have the class now.
Okay.
Okay, and of course you can reach us, any one of us. Okay, in whichever
Yes.
platform you like. Okay, I think you already have our contact numbers. So any query, whatever questions you have, you may ask later. So let's just focus on this particular experiment. You have any query, or this simulation is clear to you? You'll be able to perform yourself? Yes, please respond. Yes, no, maybe, not sure.
Please respond. Otherwise, how will you cooperate with us? Interaction is very important.
I think they are not sure.
I
Okay,
think they're giving the test, I guess, attendance test. Yeah, someone has written yes, yes, ma'am. Yeah, yeah. They are writing in the chat box.
okay,
Fine.
okay, okay. Okay, then, yeah, thank you for your response. Thank you. Then, I will show the last one, the simplest one. Okay, so you have got up to this part, and what we'll be doing next is, see, read that. Implement 4-bit parallel adder subtractor unit using full adder IC. The same thing. We are using the same full adder IC, but this time we'll be doing both addition and subtraction with the same circuit. Understood? The problem. Okay, let's. So the problem is performing both addition and subtraction using the same the 4-bit adder IC 7423. Okay, so this problem has the clue in XOR truth table. You wonder why, or you can already see the solution. See what we did. You see the XOR, okay? If x2 is 1, it is complementing the bits. If x2 is 0, it is passing the bits as it is. Right? So, this is the circuit. So, now, for now, as we were performing subtraction, so statically we connected these pins, the other, like the other inputs, to a VCC voltage power line, 5-volt line, say. But when we are trying to make a adder subtractor unit like combo, then we cannot make this connection like this, static like this. Okay, there need to be a control line. The control line should be able to tell us that which operation we are going to perform. Okay, one single line should be responsible to take care. Okay, we call that the control line. So you see there is one more thing. For subtraction, we need to set the carry C0 as 1. We saw, right? Why we need C0 as 1. But for addition, on the other hand, we do not need C0 as 1. We need C0 as 0. So let me see. I just made a partition here. I'm going to show you the addition. Say I'm going to add 3 with 15, okay? So I should get 18. Alright. So in that case, we should get, after the XOR operation, we should get 3 itself. XOR should not change my 3 to something else. Okay. And then the C0 should come as 0. Okay. And then what will be the, sorry, let's write all 4 bits 0. Okay. And then what will be the result of this addition? Result will be like 110. Then there is a carry, so 1111. And then there is 0. 10. There is a carry. So there is a 1. So is 16 plus 2, 18. So this evaluates to 18, right? 15 plus 3 is 18. So it is validated. The output is correct. So this is a simple addition. This is a subtraction. So what is the difference? Here x2 is, that is the other input of XOR, is set as 1, set as 0, and E0 is set as 0 as well. Whereas here, in here, x2 was 1, and okay, need some more space. And here uh, E1 is 1, right? Okay, understood? See the similarity? So we can basically combine this C1 and X2 inputs to one line and call that a control line. Okay, so let's do it in the circuit. Okay, so what we are going to do is, let's have a control line. This is 1100. This is 0. Okay, let's uh, something better. I'm deleting the inputs because now it should go into a control line. Okay. Why it's not happening? Okay, okay, and this C0 as well. Okay, I have freed it. Now I'm going to have a say control line. So let me just make it a. This is a label. Now I will change it. Rotate. So just think. So just think this as some terminal. Okay, I have not given any input to it right now. And this is your C0 that is going to the same line, and I'm changing its level as control line will say add. It will add when the line is uh, 0, and it will subtract. Line is 0. I'm using this tilde for denoting complement. Okay, and it will subtract when the line is high. Okay, so let's just rotate. Okay. Anyway, I hope you understand. Okay. So this is the control line. So whenever it is going to be high, it will perform subtraction. If it is low, it is going to perform addition. Now let's verify it. All other inputs are same. We are still applying 3 as the original B input. You can verify here. This is the VCC. So you can see the other inputs. These are 0, 0 and this is 1, 1, right? So 3 and here for A we have applied 15, 1, 1, 1, 1 and the control line input I have not applied anything yet. Okay, so let's apply something to it. Which operation you want to perform first? Addition? Okay, I would like to perform addition first. Okay, so let me see. I have taken a power. Okay, rotate it a bit. Yeah, and let's connect to the power. Okay, now, okay, I'm sorry for addition. I told I'm going to do addition, I'm doing subtraction. Sorry, ground. Yeah, so ground. Yes. So control line is now 0. Okay, control line value is now 0. So it should perform addition. Let's see. Can you see the output? It is doing the same thing. Okay, 15 plus 3. What happens? 18. 18 is the result, right? So carry 4. C4 is 1. You see the notepad. C4 is 1. This is carry. And this is the 4-bit sum. And the second bit, that is the second position, is on, right? So we get 18 correctly, right? Okay. Now say stopping the simulation and deleting it, okay? And say now I want to give this power input to see if the subtraction works as well or not. Okay, let's just add that. Right? Good. Now let's see. Let's do the simulation. Save it. Okay, so we ignore this while subtraction and just take this bit, some bits, S bits as the result. So you have S4, S3 on and S2 and S1 0, right? So this is 12 in decimal, correct? So it got validated, right? So this same circuit is performing both addition and subtraction. Only one thing, either we are giving a high input on this control line or a low input. A high input will do subtraction, a low input will do an addition. And now you know why. Correct. Questions? Is that clear?
Shuchina ma'am, should I stop the recording of the meeting right now? I think you have done the
Yeah,
explanation.
you may. Yeah, you may.
Okay, thank you.
Okay. All have given